So when we last left off, we were talking about skeleton equations and how to take a word equation and draw it out using formulas and subscripts for state and all that kind of stuff. Okay, so if you don't remember that, go back, take a look at the worksheet on page that would be 55 and 56 of your note package. Okay, go back, take a look at page 55 and 56, and make sure that you know how to do a word equation and then know how to do a skeleton equation from there. Okay, so it takes into account all the stuff that we've been doing up to this point. So you need to know how to write a chemical formula. You need to know how to write ionic formulas using polyatomic ions, and you need to know how to write molecular formulas with the mono and the di and the tri and all that kind of stuff. So make sure you know how to do that because you are going to be asked to do that eventually. Okay, so today what I would like to talk about is the conservation of mass. So I introduced you to this guy, Antoine Lavoisier, and he did some experiments where he measured very precisely the mass of his reactants. So that's the stuff on the left-hand side of the arrow, the things that are reacting together. And then he would react them and he'd get something brand new and he would measure the mass of that. And what he found is that the mass of the things that he started with, when he added them together, was equal to the total mass of the things he ended up with. So in other words, the total mass of the reactants equals the total mass of the products. Okay. Now, sometimes that's hard to understand. Like if for example, if you take some gasoline in your car engine and you light it on fire and it reacts with the oxygen in the air, there doesn't seem to be anything that comes out of the tailpipe, right? But if we collected the gases that came out of the tailpipe, they would be carbon dioxide and water vapor. We could collect them, we could condense them, and we could measure them, and they would equal to the mass of the gasoline that you started with and the oxygen in the air. Okay, and the reason for that is because mass is neither created nor destroyed during chemical or physical reactions, or matter. Okay, matter is not created or destroyed during chemical or physical reactions. We have to have the same atoms at the end that we started out with. Okay, so in other words, when we talk about the conservation of matter or the conservation of mass, what we're saying is that we have to have the same numbers and the same types of atoms on each side of the reaction. Okay, so here I have methane. So again, we've talked about methane, and methane is what we burn in our heaters. Okay, if you have a stove at home that is natural gas, that's what we use. This is methane, CH4. Okay, and it's a gas. When we burn it, we combine it with oxygen gas, and what we get is carbon dioxide gas and water vapor, okay, water gas. So if we take a look at the atoms, the number of atoms, okay, so this is my molecule of methane. What I'll notice here is that I have 1, 2, 3, 4 hydrogens, okay, so the green are hydrogens and 1 carbon in the middle there. Okay, so if I have 3 hydrogens and 1 carbon on the reactant side, that means on the product side, I would have to have the same. But if I go take a look at here, and basically a chemical reaction is just rearranging the atoms. Okay, so I have 1 carbon bonded to 4 hydrogens over here. Here I have oxygen gas. I have 1, 2. Remember, oxygen is a diatomic element. Okay, so when it's in molecular form, it exists as 2 atoms. Okay, now if I go over here and count the atoms, I only have 2 hydrogens, right? But I started out with 4. And over here, I only have 2. Okay, I started out with 2 atoms of oxygen over on the reactant side. And here I have 1, 2, 3 atoms of oxygen. So according to Lavoisier, this is not conserving matter. And if we measure them, we wouldn't be conserving mass either, right? So what's going on here? How am I going to rectify this? How am I going to make sure that I have the same number of atoms on each side of the equation. Okay, so what we're going to be learning today is how to use these numbers in front of our molecules in order to balance out a chemical equation. Okay, so when I add these coefficients, they're called, okay, coefficients in front, what that does is it multiplies the number of atoms that the coefficient is in front of. So if I do that, what I find here is, let me just, okay, so now I have 1, 2, 3, 4 atoms of hydrogen on one side bonded to my carbon. Okay, here I have 1, 2, 3, 4 because I added in an extra oxygen. So now I have 2 oxygen molecules. Okay, and what that does is now I have 1, 2, 3, 4 oxygens over here, and I added in another coefficient in front of the water, and I have 1, 2, 3, 4 hydrogens. So it's now balanced. I have the same number of atoms on each side. I have 1 carbon on each side, I have 4 hydrogens on each side, and I have 4 oxygens on each side. Okay, so balancing chemical equations is an incredibly important skill for you guys. In Chemistry 20, you guys will be doing this constantly. When we start to write chemical equations, it's really important for us to be able to balance them. Balancing, aside from actually being able to write the actual chemical formulas, this is the most important skill that you're going to develop in science and chemistry. All right, so balancing equations. This is going to be done the same way. There's a bunch of rules here that we're going to have to learn. And again, like everything else, it requires lots of practice. So you are going to be getting homework. But luckily, you have a lot of time on your hands right now. So, it might be a good distraction for you. But yeah, there's going to be a lot of practice here. This is a skill that's really important. Later on in Chem 20 and Chem 30, you're going to be doing all sorts of calculations, and it's really important that your formulas are balanced. Okay, so the first thing that we have to understand about chemical formulas and balancing them is that we're using these things called coefficients. Okay, now coefficients are numbers that are put at the front of a chemical formula, and they apply to the entire formula. Okay, so if we put this 2 in front of the H2O, what that means is that we are multiplying both of the atoms in this compound by the coefficient. Okay, so in other words, the 2 here applies to the hydrogen. So I would times this by 2 because there's 2 already here. That would make 4 hydrogen atoms, and I would multiply the oxygen by 2 as well. So that would mean that there would be 2 oxygens. Okay, so in 2 water molecules, that's what the 2 means, that there's 2 water molecules. Okay, so there would be 4 hydrogens and 2 oxygens. Now, to balance an equation, the first thing you need to do is write the skeleton equation, including states. Okay, now in the homework that I'm going to be giving you, for the most part, that's done for you. In the examples that I'm going to be doing, that's done for you. But don't forget the rules for writing skeleton equations. Okay, we have to include the states, and we have to make sure that we pay attention to things like, diatomic elements like oxygen and nitrogen, um, fluoride, that sort of thing. Okay, remember those. Hydrogen is another one, right? Sulfur and phosphorus, those have multiple atoms inside inside an elemental. Like for example, if you had a bunch of sulfur sitting on the table, right? That's not just written as S solid. We have to write that as S4, right? Or is it S8? I think actually it might be S8. I think I'm wrong there. Let me check my table. It's been a while. Yeah, no, sorry, that would be S8, right? So sulfur is S8, phosphorus would be written as P4. Okay, so remember the rules of writing your skeleton equation. Now, the next thing we do is we have to count the number of atoms of each element on the reactant side, and then we have to count the numbers on the product side. Okay, if they're different, then we have to start adding coefficients and retallying as you go so that the numbers are balanced. This takes a little bit of guess and check sometimes, but eventually you'll get pretty good at it. So there are some rules here, okay? So we're on page 57 there at the bottom, and as we work through this, the rules will start to become more second nature to you, okay? And again, we're going to work through some examples here, and you know you'll see how the rules apply. So number one, you place the coefficient in front of the chemical formula, not in the middle, not at the end, at the front. Okay, and what this does is it multiplies all the atoms in the formula by the value of the coefficient that you're adding. Okay, something that's important when you have nothing in front of your molecule. Okay, when there's no number in front of the molecule, we assume that it is a 1. Okay, can't have a 0 because then it doesn't exist, right? Anything times by 0 is 0. Coefficients must be whole numbers, no decimals, no fractions. Okay? Don't change the subscripts in the chemical formula. All right? So for example, if I have CO2, okay, I can't change this number. I can't make it CO3 or CO4 or just CO because that changes what the molecule is. All right? So that's why we add numbers in front when we need extra atoms. So you can never change the subscripts. Okay, don't place coefficients between atoms in a formula. So for example, don't put a 2 here, you know, if I need to just multiply my oxygens. Okay, we can't put numbers in the middle of our chemical formulas. Okay, if there's polyatomic ions on both sides, okay, you balance them as if they're a single unit, and I'll get to that more later when we try the examples. Okay, start by trying to make any odd numbers of atoms even. There's little tricks that'll help you. Start with atoms other than hydrogen and oxygen. So leave hydrogen and oxygen till the end, okay, especially in a type of chemical reaction called hydrocarbon combustion. Again, we'll talk more about that later. And balance elements last. So if you have an element like oxygen, O2, or H2 or N2 or whatever, leave those till the end. And that tends to make it a little bit easier. Okay, and then when balancing hydrocarbon combustion, start with carbon first, followed by hydrogen, and finally oxygen last. And again, I'll tell you what I mean by a hydrocarbon combustion. These are easily recognizable reactions that have a certain kind of formula to them. Okay, and we'll see how to recognize those in a minute. Okay, let's start with an easy one. Okay, so this is N2 gas plus H2 gas is equal to ammonium. So what we do is, here's the arrow. So I'm going to split my reactants and my products. Okay, so over on this side are my reactants. Okay, and over on this side are my products. I know that it's split because of my arrow. So I'm going to just kind of make a line here to denote which is which. And then I'm going to count the number of atoms. Okay, so over here I have nitrogen atoms and I have hydrogen atoms. Okay, notice I'm not writing the formulas, I'm just going to be counting the number of atoms. Now over here, I also have nitrogen atoms, okay, in my ammonia, and I have hydrogen. Okay, so according to Lavoisier, I have to have the same numbers. They're rearranged, but I have to have the same numbers. So over here, this 2 means that I have 2 of these atoms. Okay, so I have 2 of those, and over here, I have 2 of these. Okay, now if I go back on the other side, when they combine, they form this gas, and that gas only has 1 nitrogen atom in it, but it has 3 hydrogen atoms in it. Okay, so that's not balanced. I don't have the same number of atoms on each side. So what I'm going to do is I want to start by trying to add coefficients at the front. Remember, I can't change these numbers. I can't change the 2's there, right? I can't change the 3. I can't add in an extra nitrogen here, okay? Because that would be changing the chemicals. So what I need to do is add coefficients, Okay, so I have 3 hydrogens over here, and I have 3 hydrogens over here. I have 2 nitrogens over here, and I have 1 nitrogen over here. So what I can do is I can add a 2 here. Okay, now this 2 it multiplies each of the atoms. Okay, so 2 times 1, right? There's a 1 there. 2 times 1, okay, now I have 2 nitrogens. And 2 times 3, now I have 6 hydrogens on this side. Okay, so what I'm trying to do is the first thing I want to do, if you look back at your tricks and rules, is try to make any odd numbers even. So what I did is I added a 2 here. 2 times 3 is 6. Okay, 2 times 1 is 2. Now if I go over here, my nitrogen, I have 2 nitrogens, so I'm good there, right? So far so good. The nitrogens balance. But I have 2 hydrogens over here on the reactant side, and I have 6 hydrogens, sorry, on the product side. So that doesn't equal out. Okay. Some of you might already have figured out, what am I going to do? How am I going to balance it? Well, if I add the coefficient 3 here, 3 times 2, okay, this now turns into 6, and it's balanced. Okay. Do I have to add the 1 here? No. If it's blank, then I just understand that there's a 1 there. Okay, so 1 molecule of nitrogen gas plus 3 molecules of hydrogen gas give us 2 molecules of ammonia. All right, and you can see here that everything balances out. All right. Now this one's a little bit more difficult. Okay, there's definitely more atoms on each side. There's more molecules involved, but it's done the same way. So separate your 2. Okay, so I have my reactants on one side and I have my products on the other side. Now let's see what atoms I have. So I have calcium. Okay, I have carbon. I have hydrogen and oxygen. Okay. Now a little bit more on that in a second. Now over here, I have calcium. Okay. I have carbon over there. I have hydrogen right there. Okay. And I have oxygen and hydrogen over here. Okay. But the thing is it's together in a hydroxide polyatomic ion. Okay. So whenever possible, I want to keep my polyatomic ions together. All right, so if I have a hydroxide over here and I have a hydroxide over here, it's much easier to balance them as just a polyatomic ion. Okay, the problem is over here I don't have a hydroxide, or do I? Now, something you guys probably don't know is that you can write water as HOH. Okay, remember, a water molecule looks like this. It's an oxygen, and we have our hydrogens on either side coming out here, right? And that's polar. So really, it's kind of like an oxygen sandwich, right? I have hydrogen on one side, I have oxygen, and then I have hydrogen on the other side. So I can write it like this. And when I write it like this, what that does is now I have hydroxide here, and I have a hydroxide here, and that makes it much easier to balance. Okay, so if you ever have hydroxides on one side of your equation and water on the other side of your equation, rewrite water so that it looks like this. Okay, HOH. So now what I can do is I'll go down here and I'll just erase. Okay, so I'm not going to have my hydrogens and oxygens separate. Okay, I'm going to have a hydrogen on this side and an OH on this side. Okay, right? So I've separated this. So now I have a hydrogen and I have a hydroxide. Okay, so I have a hydrogen and I have a hydroxide on this side. Okay, I have my calcium, I have my hydroxide on this side, I have my carbon over here, and I have my hydrogen over here. Okay, so I have the same types of atoms on each side, but I don't have the same numbers. Or maybe I do. I don't know. I have to count them. Okay, so how many calciums on this side? Well, there's no number here, so there's 1 calcium. How many carbons on this side? Well, that coefficient only applies to the carbon. It does not apply to the calcium, right? So I have 2 carbons over here. Okay, remember I rewrote water. So forget water in this way. I rewrote water as 1 hydrogen and 1 hydroxide. So I'm only going to say that I have 1 hydrogen on this side. Okay, because remember, I'm not even going to look at it like this. I have 1 hydrogen right here. And then how many hydroxides do I have on this side? I have 1 hydroxide. Okay, because I'm going to keep the OH together. Now on this side, okay, I have 1 calcium. Oh, look. So why do we use brackets? Some of you are like, oh, what's the big deal if I don't have brackets or not? Well, now that I have brackets around this hydroxide, this 2 here applies to the whole thing in the brackets. So I have 2 hydroxides over here. Okay. Here, this 2 applies to just the hydrogen. So I have 2 hydrogens over here, and this 2 applies to the carbon. So I have 2 carbons over here. Okay, so it's definitely not balanced. Oh, what did I do over here? Sorry, guys, I'm kind of getting used to all of this myself. Okay, so sorry, I only have 1 hydroxide over here, right? This guy right here in the water. All right, so I have to get to balancing. So my CAs are balanced, my carbons are balanced, but my hydrogens are not balanced. Okay, so I have 2 on this side, and I only have 1 on this side. So my hydrogens are found in my water over here. So if I add the coefficient 2, that 2 is going to apply to my hydrogen and to my hydroxides. Okay, so now go back, I scribble this out. I now have 2 hydrogens on this side, and I now have 2 hydroxides on this side. Okay, so I think if I look here, okay, 1 calcium, 1 calcium. Remember, this 2 only applies to the hydroxide. I have 2 carbons over here on this side, great. And I have 2 carbons on this side, perfect, okay. Now I split my water into H's and OH's. Okay, so this 2 tells me that I have 2 hydrogens. Perfect. And over here, this subscript tells me that I have 2 hydrogens. Perfect. Okay, OH's, this 2 applies to the OH's. And no, I don't need brackets around there because there's only 1 OH in the water molecule. When I put the 2 here, though, now there's 2 OH's overall. Okay, and this 2 right here tells me that I have 2 OH's. Perfect. So this is now balanced. Okay. All right. So again, we want to treat the polyatomic ions, if we have them on both sides, we want to treat them as single units, okay, like we did with the hydroxide in the last one. So again, split my sides here. So I have hydrogen, okay, right here. I'm going to keep the PO4 as PO4. I'm not going to split it into P's and O's, okay, because I have a PO4 over here and I have PO4 over here. So don't split them up. Keep them as one unit, PO4, okay? Now, if I didn't have them on both sides, then I'd have to split them up, but I do, okay? Calcium, and again, SO4. Don't split it up if you don't have to. So do I have an SO4 over here? Yes. Okay, so keep it the same. Okay, so SO4. I have SO4s on both sides, I have calcium on both sides, I have PO4s on both sides, and I have hydrogens on both sides. Okay, so again, over here, I have hydrogens, I have PO4s, I have calciums, and I have SO4s. Okay, so now we go and count them. So on this side here, this 3, this subscript, only applies to the hydrogen. So I have 3 hydrogens over here. Okay, there's no brackets around the PO4. Okay, so there's only one PO4. No number next to the Ca, so there's only one Ca. And again, no brackets around the SO4 or anything, so there's only one SO4 on this side. On this side, two hydrogens, excuse me, one SO4, three calciums, and now I have a 2 here. The PO4 has brackets around it, so that 2 applies to everything inside the PO4. Okay, so there are 2 PO4s. Okay, so now I have to get to balancing. So let's try to make, I don't know, let's try to make our calciums even. Okay, so I have 3 calciums on this side. Oh, but hold on, I only have one SO4. So if I put a 3 there, so a lot of this, guys, is kind of guess and check. Okay, let me just erase some of this stuff so that we just have some, so it's kind of clean here. All right. Okay, so a lot of the times, some of this stuff is just guess and check, and I'll have to go back and kind of mess around with it a little bit just to make sure that, I'm making the right choices as far as coefficients. Okay, so let's I don't know, we got 3 and 2 hydrogens, calcium's, phosphorus. I don't know. Let's go ahead and take a look at your rules. It says, start by trying to make any odd numbers of atoms even. So let's try to make our calciums even. Okay. So 4 on each side, 1, calcium's on each side, 3. So let's go by putting a 3 here. Okay. So what does that do all of a sudden? Well, what it does is it now makes me have 3 calciums, and this 3 applies to the SO4s because I'm keeping them together, right? So now I have 3 SO4s on this side, and I have 3 calciums on this side, okay? So we keep plugging away at it. So now I have, so this is balanced at the moment. That could change. Okay, so now I have 3 SO4s over here, and I only have 1 SO4 over here. So how do I change that? Well, I can put a 3 here. Okay, so that changes this to 3. All right. But now that's going to also change this number. So 3 times 2, right? That now gives me 6 hydrogens on this side. So now let's go over here. Okay, what if I put a 2 here? So that 2 is going to apply to my hydrogens. So 2 times 3, now I have 6 over here. And this 2 is going to apply to my PO4s. So I only had 1 PO4 in this acid here. Okay, so now that's going to change this to 2 PO4s. Okay, so let's take a look. Okay, 6 hydrogens on each side. Yep. 2 PO4s on each side. Yep. 3 calciums on each side. Yep. And 3 SO4s on each side. Yeah. Okay. So remember, guys and girls, we are treating these polyatomic ions as one thing. So yeah, if I wanted to expand it out, it would be 3 times the sulfurs and 3 times the oxygens. I have 12 oxygens and 3 sulfurs, right? But it's a mess over here. So just keep it together as an SO4 if I have an SO4 on this side. So it's easier to count it as 3 times the SO4s. So I have 3 SO4s over here. 3 times the SO4s, I have 3 SO4s over here. So that's balanced. Okay, so whenever possible, keep your polyatomic ions and count them as one unit. Okay, so earlier I was telling you guys about hydrocarbon combustion reactions. Now, hydrocarbon combustion reactions are whenever we have something called a hydrocarbon. So a hydrocarbon literally has just hydrogen, okay, has hydrogen and carbon. Sometimes there'll be oxygen attached to this as well, but a hydrocarbon basically just has carbon, hydrogen, and sometimes an oxygen. Okay, now you'll be able to recognize hydrocarbon combustions because this hydrocarbon always comes first, okay? And then it's reacted with oxygen gas every time, okay? That's how you're going to tell it's a hydrocarbon combustion. And the reactants are always the same. They're always carbon dioxide and they're always water, okay? So an example of this would be cellular respiration, where we take sugar, which is C6H12O6, okay, glucose, plus oxygen gives us carbon dioxide and water. Okay, propane, same thing. Butane, which you find in cigarette lighters. Octane, which you find in gasoline. It's always the hydrocarbon plus oxygen gives us carbon dioxide and water. Okay, and that's known as a hydrocarbon combustion. So these can be a little bit tricky because you can get really big numbers, and sometimes they just don't balance very easily. So there's kind of some rules that we start with, and then if we have to, we can ad lib later. But if we follow these rules, they generally make hydrocarbon combustion balancing a little bit easier. Okay, so again, we're gonna divide our reactants and our products. Okay, so carbons on this side. Okay, we have hydrogens on this side, and we have oxygens on this side. So I don't have any polyatomic ions, right? So I don't need to keep any together. Okay, right? There's no polyatomic ions on this side and then on this side. Okay, do I have to change my water to HOH? No, I only do that if I have hydroxides on one side, right? And I don't have hydroxides on the other, then I can change my water. But I don't need to change water in this reaction. Okay, so again, over here I have carbons, I have hydrogens, and I have oxygens. Okay, so when you're doing hydrocarbon combustions, what we want to do is we want to start with our carbon first. Okay, so over here I have 3 carbons, I have 4 hydrogens, and I have 2 oxygens. Okay, over here I have 1 carbon, I have 2 hydrogens. Okay, now this one's a little bit tricky. So over here I have 2 oxygens, and over here I have 1 oxygen. So I have to add them together. I have 3 oxygen molecules. Okay, so start with your carbons first. So I have 3 on the reactant side. I have 1 on the product side. So if I put a 3 here, okay, that 3 applies to this carbon. So this changes to a 3. Gets changed to a 3. And then this guy right here, 3 times 2, that's going to give me 6, right? So 3 times 2 is 6, but don't forget this oxygen over here. So I have 7 oxygens on this side. Okay. Now let's do the hydrogens next. Okay. So I have 4 hydrogens over here on the reactant side, and I have 2 hydrogens on the product side. So, okay, what I need to do is add a 2 here, right? So now 2 times 2 gives me 4 hydrogens on this side, okay? But that's now going to affect how many oxygens I have, because this goes 2 times 1, okay, is 2. So now I have 2 oxygens over here, and I have 6 oxygens over here, right? So that's actually going to make 8 oxygens, right? So 3 times 2, okay, this is going to give me 6 oxygens over here. 2 times 1 is going to give me 2. 6 plus 2 is 8. Okay, so I balanced my carbons first. I balanced my hydrogens next. The last thing I want to do is balance my oxygens. So I have 8 oxygens over here. I have 2 over here. So all I do is add a 4, and that's going to turn this into an 8. And now 3 carbons on each side, 4 hydrogens on each side, and 8 oxygens on each side. Okay, so trust me, ladies and gentlemen, hydrocarbon combustion reactions can really give students a big problem if they don't follow these rules. All right, so carbon first, hydrogen next, and always leave your oxygens till the end. Okay, now there are 3 practice problems in your notes. So on page 58 of your note package, There are 3 practice problems, and what I would like you guys to do is right now take some time and work through those reactions, okay? Balance them. Work on those 3 practice problems on page 58 of your note package, and then we'll go through them together. Okay, so hopefully you actually took some time and worked through those practice problems. You know, just watching me do it is not going to help you. You actually need to practice these things. Okay, so hopefully you've done them. Maybe you've been stumped, and that's okay because that's what we're going to work through right now. Okay, but make sure you do these. Don't just follow along with what I'm doing. Do them on your own, and then we'll go through them together. Okay. All right, so you've all done them. So now let's go through them. Okay, so start by dividing your reactants and your products. Then the next thing you want to do is write out the types of atoms you have on each side. So I have magnesium over here, I have hydrogen over here, and I have chlorine atoms over here. Okay, over here, same thing. Magnesium, magnesium, hydrogen, and chlorine. Okay, so not only do we need the same types of atoms, we need the same numbers. So there's no number here, there's no number here, so I just have one magnesium. Okay, how many hydrogens do I have? I have one atom of hydrogen. How many chlorines do I have? I have one atom of chlorine. Okay, over here on the product side, one magnesium. This 2 right here does not apply to the magnesium, only the chloride. Okay, so that means I have 2 chlorides over here and I have 2 hydrogens over here. Okay, so how am I going to balance this? Well, this one's fairly easy because if I put a 2 right here, okay, now what I've done is I've doubled the number of hydrogens and I've doubled the number of chlorides. Okay, so now I have 2 hydrogens on this side, and now I have 2 chlorides on this side. So my magnesium's balance, my hydrogen's balance, and my chlorine's balance. Okay? So I started with an easy one to warm you up a little bit. Okay, next one. So again, divide the 2. I want to count the types and numbers of each atom on each side. So I have iron, copper, and chlorine. Okay, and I also have iron, I have copper, and I have chlorine on this side. Okay, so how many irons do I have? 1. How many coppers do I have? Just 1. How many chlorines atoms do I have on this side? 2. Okay, over here, how many irons? 1. How many coppers? 1. How many chlorines? 2. Sweet, it's balanced already. I don't have to do anything. Okay, so same numbers, same types, and it's balanced. Okay, it's already balanced. Okay, last one. This is how we make water. Well, we don't make it this way, but the universe made it this way. We take hydrogen gas, take oxygen gas, and add a little bit of energy, and boom, you get water. Okay, and like I think I mentioned this in class, this is kind of what some people are saying is the future of automobiles, is if we can figure out a way to get a reliable source of hydrogen gas. I mean, oxygen is all around us; it's in the air. This makes a big boom when you do this, and it's more than enough power to power a car, for example. Okay, we just need to figure out where to get the hydrogen from and how to store it safely because it is very explosive. Okay, so again, I'm gonna just now, is this a hydrocarbon combustion reaction because I have oxygen on this side and I have water on this side? No, it's not. Okay, I'm missing the hydrocarbon on the product side, and I'm missing carbon dioxide on the reactant side. So this is not hydrocarbon combustion. Okay, so I have hydrogen on the reactant side, I have oxygen on the reactant side, and I have hydrogen on the product side, and I have oxygen on the product side. Why am I not writing this as HOH? Because I don't have hydroxide over here. Okay, Only write water as HOH if you have hydroxide on the other side of the equation. It just makes it easier, okay? So I have 2 hydrogens here, I have 2 oxygens here, I have 2 hydrogens here, but I only have 1 oxygen here, okay? So I'm going to add, try to make odd numbers even. 1 is an odd number. So now I have 2 oxygens, right? 2 times 1 is 2. 2 times 2 is 4. Okay, now my oxygens are balanced, but my hydrogens aren't. So if I add a 2 in front here, then this becomes a 4, and I'm balanced. Okay, so remember, ladies and gentlemen, this is not a 0 here. There's a 1 here. So on a numerical response, if we ever get back to class and you're writing a numerical response, and I ask you to put it in numerical response, right? So here's your numerical response. Oh man, that's terrible. I promise I'm not drunk. How would I bubble this in? This would be bubbled in as a 2, 1, 2. Okay, so even though there's nothing in front here, it's still counted as 1. Okay, all right. So what I would like you guys to do now is work on check number 6 to 9 in your textbook. Okay, page 90 of your textbook. So number 6 to 9. And then if you flip in your note package, worksheet 8 is balancing equations. Okay, there are 20 there. And then on the back side, I want you to actually write the word equations, the skeleton equations, and then balance them. Okay, now I'm going to tell you guys this right now. If we were sitting in class, this is probably where the most confusion comes in. Okay, so I would have students during my PETs getting extra help. Balancing equations is tough. So I need you guys to practice. Okay, remember all the answers are posted on my Google site. All right, so go on there and take a look at the keys and come to me, via email and say, Mr. Forestier, I don't get this. Could you go over it? And I will go over it. Okay, so good luck.